almost caught up now with, I guess, David setting the questions, which is good, I guess. So that means I think we've only got 6 to go through today. So let's make a start with 8.6. This is more of the stuff about manipulating distributions and using basically matrix algebra to show some interesting things about the normal distribution. And question 8.6 says you need to derive result 8.5, which is actually not really hard to find, but it's on page 179 if you've got a printed copy of the book. And the result 8.5 says that the expectation of this quadratic form, where x is a normally distributed variable, is in fact equal to the quadratic form of the mean plus a trace of the covariance matrix. And you're given this hint in the question that you're going to have to use this identity x transpose ax is equal to trace a outer product. And so this fact follows quite easily actually, because this is just a number, right? So this is a matrix, right? This is a vector, a row vector because there's a transpose. This is a matrix A, and X is a vector. So when you multiply these things together, you just get a number. So because of that, we can just take the trace of the thing, because the trace of a number is just a number. And the rule of the trace is that actually you can commute the things inside the trace. So that's how you get that identity. Anyway, so we need to show that thing, which we can do by basically doing the same thing, right? So I claim that, I'm going to take the left-hand side here, and I claim that, well, this is just a number. This is the expectation over x of the number. So I can just take the trace of it, and it's the same. So if I take the trace of this thing, I'm going to drop this. I mean, it's still sort of there, just not writing it. So this is true because it's just a number. But the fact about integration, as you all know, so by the way, this is the expectation, so it's an integral of this thing over this distribution, right? The fact of integration is that it's happy under linear transformation, right? So we can break it out, and the trace is just adding up all the things in a matrix. So I claim that we can write this actually as the expectation of the trace. Okay. And now we can use the fact about trace that we can commute these things. And so I can write this as right. So yeah, the point is that I can take the trace of this thing and go from that to that. Right, sorry, I got a little bit confused here, right? So now this, but commuting those things in here, we can write as A XX transpose outer product. And then we have this fact also, it's not given in the question, but you should probably know this, that the covariance matrix is equal to the expectation of this outer product minus the outer product of the means. So if I plug this in, we can write this is equal to the trace of A sigma, hello, plus A mu. And now we're almost there. So I can write this as trace. Again, because it's happier, trace is just adding up the numbers, so I can separate these out. Two separate traces. Just trace A, mu, product. But this, I just use this fact again, and I could write this as trace A sigma plus mu quadratic form, and that's result equal to 8.6. Question 8.6, result 8.5. Right, 8.11 is the next question. Question 8.11 is about integrating a multivariate Gaussian. So last week we derived the normalization constant of a univariate Gaussian. Today we're going to do it for the multivariate Gaussian. So we're interested in this interval I, which is just the normalization constant of the Gaussian function. X minus mu transpose sigma inverse x minus mu with respect to this vector x. So we're told in the question that we're going to use a transformation z, which is going to be sigma minus half x minus mu. And of course the reason we're interested in this thing is because it allows us to turn this quadratic form into z transpose z. So that's why we're interested in this transformation. And in order to do the transformation, we need to work out the Jacobian, and it turns out that the Jacobian is that sigma to the minus a half. And so we just change the variable. So we can write this as the integral. And the limits, I think, stay the same because this function is going to change the limit x minus half z transpose z times by this Jacobian with respect to z. And the trick now is to notice that this product here we can write just as a sum in the individual components of z. So this is just a sum over I, where I is indexing the things in z. Zi squared. So that means that we can write this as a big product. So I'm going to pull out this term because it's constant and not dependent on z, so that's going to come to the front here. It's det sigma is minus half. Now, because I've got the sum in this integral, sorry, in this expectation, I can actually write it as a product by pulling it out. You see what I mean? So I'm going to write this as a product over I of the integral x to the minus 1/2 zi squared with respect to dzi. Okay. And, well, we already know this from what we did last week. So we can write this out as second start times I and so this just gives us, sorry, this should be I over 2. This just gives us the thing that we would expect from multivariate Gaussian, because I presume we've already seen the multivariate Gaussian distribution function. It's actually the square root of det 2I sigma. And that answers the question for that. Okay, so the next question is question 9.1. I'm going to come back to that at the end because I'm going to use the MATLAB to go through question 9.1. So I'm going to skip to question 9.2. Question 9.2 is about maximum likelihoods for Gaussian distributed variables. So we're given, we're told that we have n examples of a Gaussian variable x. So they're called xn, or n equals 1 all the way up to n. And we're interested in working out the distribution posterior for x, having observed all of those things. So we need to consider, and we're taught to do that by maximum likelihood, so we need to consider the likelihood function for x. And so I'm going to write the probability of our observations, which I'm going to just put in this vector x. Well, they're all independent. I think we're told that in the question. We're not, but let's assume they are. It's a product over this n of each individual x. And we're told that this is a Gaussian. So we write this as a product over n of this Gaussian function, given some mean and some variance, sigma squared. We are interested in estimating mu and sigma squared. So in order to do this, we need to maximize this function by choice of mu and sigma squared. And actually, it's easier to do it by taking the log likelihood, just algebraically. It's much easier to work with. And we can do that because log is a monotonic function. So when we maximize the log, we also maximize the function. So I'm going to take L to be log of this thing, which looks like this. So instead of the product, I've now got a sum. It's just the law of logs. So I've got a sum over n. And I'm going to take the log of this Gaussian function, which is going to have, so it looks like that, right? So I'm going to get rid of the x because I'm taking the log. So I have minus 1 over 2 sigma squared, x minus mu squared. But of course, I also have the normalization constant in the univariate case. So that's going to give me this minus log the square root of 2 pi sigma squared term. And this is for each n. Okay. And I'm going to use law of logs again here, because I can write this. So instead of minus log root 2 pi sigma squared, I can write this as minus log root 2 pi. Sorry. Yeah, that's fine actually. But I'm going to take out the square root and bring it out the front and write this as a half log sigma squared. This is just the law of logs. So now I have this likelihood or log function, and what I'm going to do is differentiate it with respect to the things I'm interested in, which are mu and sigma squares, and now I'm just going to find a stationary point by setting it to 0. Classic optimization. So derivative of L with respect to mu. That's pretty easy, right? Because the only mu terms that are in here. So I'm going to keep the sum over n. And the derivative of this thing is going to be minus 2 over 2 sigma squared. So I'm bringing this 2 from here. And the derivative of this respect to mu is minus 1, so this becomes a plus. And then I have x to the n minus mu. Okay, so this cancels. And by setting this equal to 0, I can see actually by rearranging it, the sigma squared is going to just disappear when I multiply by it, and what I'm left with is that minus the sum over n x to the n, and then I've got n lots of mu. And so now what I do is rearrange this, and I get the mu is equal to the average of the observations, which is what we might expect. Sorry, this should be capital N, right? Okay. And for sigma squared, we basically do exactly the same. It's a little bit more difficult, but not the end of the world. So dl the sigma squared. So I'm going to differentiate with respect to sigma squared rather than to sigma, which is fine. You just need to get your head around it. And this is going to be sum over n again. So I've got a sigma squared on the bottom here. So this is going to become plus y over sigma to the 4. And this is just a constant. So now I'm going to consider these two terms, which is what I wrote instead of this. Well, this one has no sigma squareds in it, so I can just forget about that. It's just a constant. This term is interesting though. So when I differentiate this with respect to sigma squared, I'm going to get minus a half, and then this will become 1 over sigma squared. So when I set this equal to 0, multiply by 2, I get 1 over sigma squared, plus the sum over n, 1 over 4 x minus mu squared. And sorry, of course, this is all inside the sum. So this is now going to have an n on the top. So now what I do is move this to this side and multiply by sigma to the 4, and I get sigma squared equals 1 over n sum over n x minus mu squared, which is what we expected, I think. Okay? let's move on to 9.3. Actually, no, let's do 9.4, then I'll go back to the because I'm going to do both of them on MATLAB. So let's do 9.4 first. And 9.4 is about some abstract belief network that's just written as what the likelihood is written as this thing. It's the sum over n, and this n is the observations we have. We have capital N of them, and the graph is given as this thing with k nodes in it. So it factorizes, because it's a belief network according to each node conditioned on its parents, but we're not told what those parents are. And we are going to define this notation, which is to say that each of these guys is given by a theta, SIT, what was xi to s, given that the parents, whatever they may be, have the value t. So it's just a choice of notation, and the reason I think David's done is just to say that actually we're going to try and treat these things as values, which is what they are. It's just it makes more sense than writing this, because this makes you think it's a function of some sort. So now we're taught to use this Lagrangian, which has got lots of Lagrangian multipliers on it. And the reason we do that is to enforce the constraint that this thing is a distribution, which means that it has to all sum up to 1. So that's where these Lagrange multiplier terms come from. So the Lagrange multiplier, so Lagrangian, is the log likelihood plus some terms, and I'm going to rewrite this log likelihood in a more useful way. If I can find it. So
sorry, what do the indices on I represent?
So here.
The I equals k.
Yes, but the balance of
This one.
Yeah, what do they represent?
So this sum is over all of the variables in the belief network. So
And then n is
this is the observations.
the okay.
Yeah. So yeah, we assume there are n observations, and then this is the one graph. So I'm going to rewrite this log likelihood using the thetas, and then add on the Lagrange multiplier terms. So we're going to have a sum over n, which is the observations that we make, and we have a sum over I, which is the nodes in the graph. But instead of having it written this way, what I'm going to do is introduce some indicator functions. So indicator functions just have the value 1, basically, when the thing in the brackets is true. So the effect is to assign the value of xn to the variable s, and also assign the values of the parents of x to t. And of course, sorry, this should have a notation. Log theta I s t. So the point of these indicator functions is just to say they're going to be 0, so they're not going to be present these terms unless the s is equal to xi n and t is equal to the values of the parents. And then we have the Lagrange multiplier terms that we've given in the question, which are sum over all of the variables k, and the sum over all of the values of the parents ti, lambda I ti. So these are the Lagrange multipliers. And then we have the actual constraint that the sum over s, these is ti, is equal to 1. So if you've never used the Lagrange multipliers before, I suggest you read up on that. It's not hard really, it's just a little for you to get your head around it. So this is the Lagrangian, but written in thetas. And what we do is differentiate this Lagrangian L with respect to each of the thetas. So we take each derivative, partial derivative with respect to theta. And if you do that, then you get one of them from here and one of them from here, I think. And those are the only remaining terms left in your derivative. So this is now just going to be the sum over n equals 1 up to capital N of the one term from this. So there's no longer a sum over k because all of the ones that are not equal to j have dropped away. So this is now the indicator function xjn equals s. The indicator function parents of xj and equals t. And differentiating this, of course, we just have 1 over theta j, sorry, it's going to be j st. And we have one term from here for each. Sorry, yeah, it's just one term from there because we no longer have the sum over n. So now this is just section minus the lambda term, lambda j, tj. And this is true for each j, and each s. So on our right, it's got a bit of skew there. So in order to find the maximum, we set this equal to 0, and then we can write that each theta jst, by rearranging this thing, is going to be equal to 1 over lambda, and then we have this sum, of course, sum from n equals 1 capital N. And we're almost home and dry, so all we need to think now is that, well, these thetas are actually these guys, so summing over s, they have to sum up to 1, because they have to be distributions, so we can just normalize them, and so we never have to actually work out what lambda is. So we'll just normalize these things, and if we do that, then we just see that you get the answer basically on the question, which is that sum over n, that's the indicator function x n j equals s, indicator function parents x jn equals tj divided by the sum over all of the s's, the same thing. and then we're done. Question 9.4. So that one's just a little bit fiddly, actually. It's not too much fun, but yeah, I think the lesson there is how to use the large multipliers and how to find the maximum of this function. So I've left behind questions 9.1 and 9.2. So maybe let's go to 9.2 first of all. Was it 9.2? Yeah, I think it was 9.2. I'm a bit confused. 9.3, sorry. So we're going to do 9.3 then 9.1. And so from question 9.2, we know how to calculate the maximum likelihood estimate of sigma squared and mu when we have a Gaussian variable. So we already know kind of what we need to do here, so I'm going to wipe everything else off. Told that there's going to be two classes of a variable x, and we're told that the probability of x conditioned on its class is going to be a Gaussian. So all we need to do, in order to find the conditional distributions by maximum likelihood, is to apply this formula, and this formula to each of the two classes. So this hopefully shouldn't be too taxing. So why don't we do that in MATLAB? We've got plenty of time. My computer to wake up. So, somewhere I have already typed this in. So we're given the x1, can you see that?
Yeah.
It's not legible. You need that.
You will probably make the fonts bigger from the references.
Fonts, that's one thing, isn't it? Let's go to 24.
Wow.
Right. So I've typed in the list for the first class. Hopefully I haven't made any mistakes. Okay. So then, in order to get the mean, I'm just going to use the function mean. So that's the mean of the Gaussian for class 1. For the variance, I'm going to calculate this, which is the sum of each of the deviations from the mean squared divided by the number of them. This is exactly this function here. And that's going to give me this thing, so that's the variance. Actually, this is a univariate Gaussian, something like this. And so that's the class 1. Class 2 is exactly the same, so I'll have to type the same as well. Somewhere. There we go. This is x2. So I just do the same thing. Calculate the mean. Which is 0.865, and the estimate of the variance, which is this thing, 0.0092. So we've got those two Gaussian distributions. Now the second part of the question It says also estimate the class probabilities, whatever this is, using maximum likelihood. And this is really simple, right? So now we need to work out what's PC, or maximum likelihood, but that's really easy because we just count them. So, the probability that class is 1, well, there are 10 things in class 1, and there are 14 things in total. So, and if you read the book, you will see that this is in fact the maximum likelihood solution, and this is just 5/7. So by normalization, the probability that the things in class 2, or prime probability that things in class 2 is just going to be 2/7. And so we are asked to calculate the probability that the test point x is equal to 0.6 belongs to class 1. So what we want is the probability that the class is 1 given that x is equal to 0.6. And guess what? We're going to use Bayes' rule. Comes a shock to you. So that's going to be the joint of x is equal to 0.6 and the class is 1 divided by the marginal probability if x is equal to 0.6. We know how to calculate this thing because you've already estimated the parameters of the distribution. I'm just going to wipe it off. So this is in fact equal to, first of all, on the top, the joint probability that x is equal to 0.6, given that it's in class 1, well, that's just a normal PDF value 0.6 with the parameters of class 1, which we just calculated as 0.26 and 0.0149. But I have the joint probability here, so I think the probability that class is 1, which I just said was 5/7. And so for the denominator, we want the marginal, and so now we need to sum over the class on the bottom. So now we're going to have this thing, which is the joint of x is 0.6 and the class is 1, the same thing again. Plus the probability that it's the joint with c is equal to 2, which is the other normal distribution that we just calculated. So that has a 0.865 and variance 0.0092 and times it by 2/7. Okay, and if I do that in MATLAB, this thing. It's very long, I'm afraid, because the font size is so big. But trust me, it's that. The answer is 0.632. And that's that. That's question 9.3. So the only one left is question 9.1, which is this printer nightmare thing, which is a bit of a nightmare question. So the first part, there's this long-winded intro. Basically it says a printer that's dodgy and there's a belief network about it with loads of different variables. At the top it has some causes which are unobserved, and at the bottom we have some observations that the reason that the company knows the printer's not working. So is there a smell of burning, is the quality rubbish, is the paper wrinkled, and so on and so forth. We're given a huge matrix of values that were observed. So here's the belief network somewhere. There's a question. Right, so there's the belief network. Then we're given this huge matrix of observations. And basically, the question is all about maximum likelihood learning in this belief network, and David has asked you to implement that using the BRL toolbox. So I'm going to show you here the solution. So, and yeah, this is a bit annoying, maybe 26 is too big. So first of all, this line, number 3, sets up the variables. So it just assigns the numbers, and then sets up the potentials. I think actually this is based on the older version of the toolkit. So if you want to use the object-oriented version, then it will look different like this. So he's just initializing here all of the potentials to be zeros. So that's just setting up the structure of the variables. And then this part here is actually doing the learning. So all it's doing is calculating from X, which is the observation matrix, the number of occurrences of each combination, adding them up, and assigning those things to potentials and conditioning the potential using this condition function here. So all it does is count the number of states. So the probability, a variable, let's pick one, fuse. Is going to be so the number with fuse equals 1 divided by the number of all of them. So all that's what it's doing. This gets a little bit more complicated when you consider the conditional potentials that you need for the variables with conditional dependencies. If you read through the chapter, then it's all very easy. And I've also here written out, so part 3 of the question says, sorry, let's do part 2 first. Part 2 of the question says, compute the probability that there is a fuse assembly malfunction, given that the secretary claims there is a burning smell, the paper is jammed, and that there are no other problems. So that's what this line does, line 36. It says, set the values of burning, jam, poor print, wrinkled, and multiple to 2, 2, 1, 1, 1. So the 2 here is 1, and the 1 is 0. Okay. So it's a little bit confusing, but so this is saying that burning is true, jam is true, and all of the rest are false. So it's setting the values of those variables, and then normalizing it and displaying the table. So if I run this function, the output of that bit is probability fuse assembly malfunction is 0, 1. So that's definitely saying that it has malfunctioned. Fuse assembly is definitely malfunctioned. Part 3 of the question says, repeat the above calculation using a Bayesian method in which a beta flat prior is used on the tables. And what I would recommend for this is that you read in the book section 9.4.2 in order to understand this properly. And there's a good example as well, which is this asbestos smoking cancer example. So this is basically what you need. That data V, and you're using a flat beta prior, which is that the beta distribution with hyperparameters alpha and beta both equal to 1. You just add the hyperparameters onto the counts. So I would read 9.4.2 and example 9.3. This is the whole thing, right? So if the line that's important here is 9.4.16. This one, that you just add the hyperparameters onto the counts. And if we do that in the case that we're interested in, then I've just written this up here. So it's exactly the same as the previous one, it adds a 1 onto every count. Okay? And if we do that, then we get a different value for the conditional probability of fuse malfunction, which is this one here. So now, actually, we're less certain that there's been a fuse assembly malfunction because of that prior, which if you think about it makes sense. And so the rest of the question is all about max absorption and what's the most likely joint state. And again, of course, this is just done quite easily with the BRL toolbox. So here we go. There's this max plot function which takes the joint potential and calculates the potential and maximal state. And when we do that, we find that the maximal joint state is, I'm sure you just saw on the screen. It's just that the fuse has malfunction, but everything else is okay. And then you can also do the same calculation using a junction tree. And lo and behold, you get the same answer, but the method is different. So this creates a junction tree, uses potential, which has all of those values assigned, as we already talked about. Do full absorption, and then output the maximal joint state. And as I said before, you get exactly the same answer, which is what we hope for. So the final part of the question is about the most likely joint state of a very similar, although slightly different, model, which is the probability of the fuse is malfunctioned, drums bust, the toner's gone, the paper's gone, and there's one with the roller. Sorry, given that there's a smell of burning, and there's a jam. And this is different because we're assuming now we don't observe the values of the other variables, which were the quality's rubbish, the paper's wrinkled, and multi-pages, whatever that means. So the question is, how can you do efficient inference in this thing using a junction tree? Well, actually, this is simple because we've already got the junction tree for the existing belief network, and the belief network for this is exactly the same, except we just marginalize out those variables we're not interested in. When we do that, because they don't have any links coming out of them, those are leaves on the tree, and so marginalizing those variables just gets rid of those leaves. So it's a smaller graph, and the inference can be done in exactly the same way, but with a smaller set of variables. And that's all. Question 9.1. That's all I've got.
Will we get the code? The code is...
Yeah, so I think David's already given you the code for the first few, right? Yeah, didn't he? I think it's on Moodle, so I'm sure he will. It's probably a good idea if you have a look at the using the toolbox.